All right, here's an example from class. Where the hell are my notes? This would normally be class 24, I believe. Yes, class 24. This year, I believe we're not doing class 24, but I'm going to do the example anyway. I have a little bit of a SolidWorks simulation to look forward to that I had created previously. All right, so this member, ABC, has mass 2.4 kilograms and is attached to this pin. And then an 800 gram, 0.8 kilogram sphere strikes the end at a speed of 3 meters per second. Knowing that L is equal to 750 millimeters, and the coefficient of restitution is 0.5. Determine immediately after impact the angular velocity of member ABC and the velocity of the sphere. A little preliminary work here. Let's figure out what the moment of inertia of the bar is going to be. 1/12 the mass, which is 2.4. And the length of it, which is going to be 0.75. Squared, or 1.1125 kilogram meter squared. And if I'm going to do the impulse and momentum diagram here, I'll go initial. I think I spelled that wrong. Initial impulse, and then final. And I will draw. Let's switch to black for the drawing. Draw. Okay. And here's the pinpoint right in here. And we can draw in our little sphere. Let's draw the sphere in here. And then the sphere. Maybe make the sphere a little closer to the tip. We're going to assume that it hits right there, and we don't worry about the roundness of the damn thing. And I'll make this right here is going to be my MD-VD1, and then right here is going to be the MD-VD2. And actually, I think I decided to treat him as if he was coming downwards. That's what I decided to do. And then we also want to have the, let's see, I guess I'll make them green. The moment of inertia. This is weird. Okay, I went ahead and did them anyway. I made my eye of that going counterclockwise, and the omega 2 of the thing going that way. I also took at the center of mass, so there's going to be M, what do I call them, ABC? Sure. ABC, and then they're going to be V, I guess I'll call it G2, right? So there's G somewhere, and there's the center of mass, 1/2 of that. And anything else? Okay, yeah, I just give a little old nod to our impulses, taking our best impulses. We have equal and opposite impulses taking here. We also have a weight impulse that we might want to just at least mention right here. The weight, delta t, if you want to call that there. Let's call it dt. It's a very, very, very small t during all of this. There's also the pin reactions that we might want to have placed right in there. Reaction dt here, and reaction right here, dt, and that's in the x direction, and that one must be in the y direction. And then, of course, we have these right here, f dt going on. Those are equal and opposite. So we're going to ignore these because it's going to be the relatively speaking, the weight is going to be small compared to what those impulsive forces are going to be. But we're going to say that it's going to be equal and opposite. We know these two are going to be equal and opposite for each other. and we're going to take care of that. One thing that we do want to know, and this is an important thing, is we're going to want to know at some point this spot right here. And I'm going to call this VA2, right? It doesn't have a mass times it. That's going to be all that's going to be taken care of by the stuff over in the bar. But that velocity is the one that really matters. Let's take care of some kinematics here. Just to try to relate some of these pieces together, we'll say that the VG is going to be related to omega ABC times L over 4, right? And that's the L, yeah, just L, doesn't matter. And then also VA, that I've just described right there, is going to be omega ABC L over 4 as well. It just so happens that there's an equal distance between here and here and here and here. That's why they're both the same thing. And the signs might matter. Now we do the angular impulse and momentum routine here. So we go ang, imp, mom, mother. Using I probably should write the equation down somewhere. It's going to be the sum of the H G1 because it's conservation right here, HG2, right? So, and we're going to say that that's going to be counterclockwise as positive. Did we decide that? Yeah. So looking up above at the initial state right there, the MdVd1, that is counterclockwise with respect to, and we don't want it to be about G. We'd rather it be about B. There you go. And then we can get rid of the reaction. That's the whole point of doing this. So we take MdVd1, and we're going to multiply that by L over 4, right? Because that's the moment arm to get to right there. Yep. And there's nothing on the left-hand side, nothing else. And then on the right-hand side, well, the impulse, that goes away because we had the conservation of angular momentum is what we're looking at. So we will keep the MdVd2, keep that as positive. And that's also L over 4. And then we will take the I, and there's going to be, let's do it, I omega 2, right? But that's also going to be plus MABC VG2 times L over 4. But we can replace a couple things here. We can replace, we can replace this guy right here. So what we're going to say here, just write the thing out again. Stick numbers inside it. Sure. Stick numbers in. 0.8, that's the number of kilograms, 3 meters per second, and it's L over 4, let's just write that as equal to 0.1875 meters, right? Because it was, right, we just divided that by 4.1875. Then we don't have to write the over 4 every time. And 0.8 VD2, we don't know. L over 4.1875 plus. Now, I'm going to pull out that omega out in here because we're going to get an omega 2 coming right into here, right? Because we're going to stick in omega 2 L over 4 right in for right there. So we'll take that I that we got up above, 0.1125 plus the mass, and that is 2.4 of the rod. And then we're moving it, that L over 4, so 0.1875 squared, right? Because that's the parallel axis theorem to get right there. And that's going to be omega 2. Writing all this out, we get 0.45 equals 0.15 VD2 plus 0.1969 omega 2, right? That's going to be equation 1. We have two unknowns, so we need the coefficient of restitution. And that's going to be E is equal to, and so we have to take a look at this, what's taking place right here. Zooming in, this, the yellow right here. That's the part that's going to matter, right? Remember, it's going to be VA2, which remember we had a relationship to right there. So we're writing out the coefficient of restitution, and it's going to be VD2 minus VA2 divided by VA1 minus VD1, or 0.5 is equal to VD2, something we want to know, minus, okay, and let's substitute right now, right in there, our 0.1875 times omega 2, right? We substituted for VA2. And I had to be careful, right, in terms of the sign convention that was going on. I'm actually kind of worried now about my sign convention, because the way that I'm drawing this with this rotation, that ought to be downwards. I'm a little concerned that I could have messed this up. That's concerning to me. You have to be careful with that kind of thing, because you're drawing this thing and you're using these sign conventions as they work through. Okay, so I'm going to continue with what I had, and I'm going to be very skeptical. I'm going to be very skeptical of that right there, because I've assumed this this counterclockwise direction, right? And my VG2 that I stuck into there assume that direction. And if I assume this omega, that means my VA2 has to be downwards, because that's in agreement with my assumption. I don't want to mix those up, so I'm a little bit concerned. So let me put that on the back burner and just continue with what the numbers I have, and then let's check. This can be kind of a confusing thing. So let's see, VA1 is 0, VD1 is 3, but it should be -3, right? It should be going in the negative direction. We should have signs in all these. So that should be a -3 right there, and I don't have it in my thing right here. So, I got this out of a book, and I'm going to take a look at this. We're going to take a look at it when we get done. All right. Let's just verify this thing. I'm not sure this is the best example in the world now, but I replaced this a couple years ago. Anyway, so we're going to get like 1.5 over here. It's going to be positive, because that's a positive 3 times there. And then we're going to get VD2 minus. But see, I'm really suspicious of whether this is plus or minus. 0.1875 and omega 2. See, I think that should be a plus right there. Okay, let me go with my new numbers, and let's see what happens. Okay? And so, if I were to, and so this is going to be equation 2, right? So here's equation 1, and there's equation 2. And let me just try to think my way through this thing. Let me write down equation 1 right here as I try to think my way through this. Live, right? I should probably pause this thing. Here's 0.45. I'm rewriting this thing out. 0.15 VD2, and then a plus 0.169 omega 2. And let me write onto this thing. Check signs. Exclamation point, exclamation point, exclamation point. So what I often will do is I'll solve one and stick it into, put it into the other, right? So if I say, I'll take one up here above, it's easier to do. VD2 is going to be equal to 1.5 minus 0.1875 omega 2, and I put that back into here, so I get 0.45. This is my really ham-fisted way of working these things out. 0.15 times 1.5 minus 0.15 times 0.1875 omega 2 plus 0.1969 omega 2. So start bringing it all over there, and I end up with 0.15, 0.1875, multiply them by each other, and then subtract them from 0.1969. And okay, so I'm going to get 0.1688 omega 2, and then let me take 0.15 and 1.5, multiply them by each other, and then 0.45, and I subtract them out. I get 0.225, and then I divide, and I get omega 2 is equal to 1.333 radians per second. And it's positive, so I'm actually saying, yes, it's going to be rotating in that direction, right? That's what I have decided that it is. And that makes sense that I'm going to hit right here, and it's going to rotate up. Okay. Did I ever make that decision right there? Yeah, I think so. All right, so I got 3 radians per second in the previous assumptions I made. But I actually have an ace in the hole right here. So let me put that down here. And then if I want to go back and find what the VD2 is going to be, because they want the sphere, right? And that's D. So we can actually plug it back into this guy. And so VD2 is going to be equal to 1.5 minus 0.1875 times 1.333, and what are we going to find? 1.5 and 0.1875, 1.333, and we're going to multiply and then subtract, and I get a positive 1.25 meters per second, I believe, right? So that's going to be, and that's going to be upwards right here. Okay. So interesting, and before I said it was 0.938, and I actually got a negative value. So I think that's where I messed up. I think both of those things need to be true right here. So let me look at a couple things. First off, let's see what Johnston said. We'll keep this for a second. Let's see, I have all the solution manuals, many solution manuals from many different books. I don't know if I actually have the 12th edition one. That's kind of weird, I know, but Johnston, I think I have the 11th and the 14th. But this is problem 1721. Let's see what this one says. I'm still recording, right? Yeah, that's good. Minute 19 into this. We can hide you. I'm just downloading it from OneDrive. Waiting for you. Come on, 5G, hurry up and get here. I don't know if that would affect my home internet. I'm not a smart man. So I'm looking for 17127. 17127. So look at all these really quick. You just probably got to check and get all of them. There you go. And what did they get? See, they got the 3 radians per second and the 0.938. So they ended up getting the same thing. But that doesn't mean they're right, just so you know. I got that, sure. It's right here that it bothers me, right? I think that 3, what did I say? I said that I think that the, see, they're calling it, they need to go that velocity right there at A. They need that velocity of A is 0 here. But I say that right here, this should be positive. Right here. That should be positive because it should be going down. We should be predicting it's going downwards based on the direction that omega goes. So VA prime, look at there. See, they're showing it as negative right there, right? They're showing it going downwards at the second time. So it should be negative right here because this right here is the coefficient of restitution, right? Yeah, actually, I don't know why they have it written out this way. This is actually weird how they've written this. Oh, no. Okay, they're saying VD minus VA prime is equal to this. Okay, that's the left-hand side. And they're saying negative, but I believe that should be negative there. Well, let's figure it out. Because I happen to have made this in SolidWorks. And what I did is there's very short duration. It's only half a second here. I don't have gravity on. I do have an initial velocity that I have placed onto the sphere right there of 3 meters per second, right? So I'm just tossing this thing in there. And if we were to go to these parts right here and look into the evaluate, we could get, not measure, we want the mass properties, and we get the mass properties, and that shows at 2.4 kilograms. I made this bar right here. Oh, and by the way, if you take it about the z-axis, let's see, it should be 0.1125, right? We need more decimal places. Let's see. Use custom units. Let's see how many decimal places they give us. 0.1187 is what they're saying. It said moments taken about the output coordinates. Taken about the center of mass. 0.1188. It's probably because it has rounded edges, right? And it actually, because it actually takes the mass moment instead of treating it like a slender rod. We could also do the same thing for this ball right here. I'm just showing you that we've given the thing properties. And look, it's got 0.8 kilograms. So I might have monkeyed around with the density to force the thing to happen. So I hit this calculate thing, and I also, I set the, here you go, body contacts, right? So we can look at this, and we can see it sets the coefficient of restitution. Even could have some friction in there if we wanted to. But I calculate the thing, and you can just do the calculation right there, right? And now we can play it at 0.1 times the speed. And we can see what's happening, right? We could definitely, just as we expect, right? Now, in terms of like measuring the things, we could plot these out. So I'm not sure what I have plotted out. I have them show. Okay, let me just show plot. There you go. And here's the values. You could see, I think, I'm not sure which ones these are. I got to double check right here. I have a plot on top of a plot, right? So I have this guy right here. It's the point. Right? Okay, so that's plotting out this one right here, that linear velocity. I'm not sure what this other guy is right here, what his purpose is, that blue one. But you can see this guy right here, he goes to what appears to be 0.9. Yeah. So there's an angular velocity. Actually, there's is that true? There's linear velocity on top of here. See, here's the problem. Let me go back and delete this graph. Yeah, just go away. And let me start with a new one. I'll go to this right here. We'll select a category, displacement. We'll go linear velocity. We'll take the y component, and if it'll let me, we'll just select this whole thing. I think so. Kaboom. Right there. Okay. So it is saying that it is going 1. Whereas, what did I say when I recalculated this other value? Let me double check right here. I said that I was predicting that it's going to go 1.25 instead of the other one I predicted it was going to go 0.9. That's interesting. That's an interesting dilemma that I have here, because I thought 0.938 was what the other, if I had treated, that's what the book had said that they're going to be. I don't know which one I believe. Let's see if we show this plot. What is that guy going to do? That showed it as being 1 as well. And let's see with the angular velocity, though. I also did plot out the angular velocity of this. Okay, it's going to... it didn't do it. Show plot. Okay, now that's messed up. Where are you? Showing plot 4, but I don't see plot 2. Show me. Show me plot 2. Show. Edit feature. Show plot 2. Angular velocity of that right there. And, okay, you're a bastard. You know what I'll do? I'll delete you too. I don't care. Delete you and show me the angular velocity. Category angular velocity by the z component is the one we care about because it's about the z-axis. And let me take this whole face right there. All right, and so what it's doing now, okay, so it always shows this in degrees per second. So that's 164 degrees per second, right? Starting out with 0. So 164 degrees, it goes 180. We divide and multiply it by pi. And I get 2.862. 2.862, and I got 3, or in the book got 3, and we're 1.33. Interesting dilemma that we have right here. What is going to be the correct answer? I'm kind of convinced that my second one is better as part of this, but we're kind of like somewhere halfway in between. This one is predicting its velocity is 1. Here, show this plot saying a velocity of 1, which is really kind of deceptive. Let's see, can we get this scale? Can we move him up? Oh, look at that. Actually, the end point right there. I don't know if I can do this with my computer. I have my computer in laptop mode here. Let me flip, or in tablet mode. Flip that over so I could actually enter a number in. Oh, it's going to get really mad because I'm stuck between 2 different computers in 2 different worlds. I might have just messed everything up in the entire world. Okay, now we're still recording. Here we are. Okay. Let me stick this as 1 right here, and the start point, let's go negative 4. And up to 1, and how come? Axis properties, going to 4. Let's go to 2. Why is it showing it that way? Major units, make them 1, make him 0.5, so we can actually see that. It still looks to me like it's on 1. Maybe it's just that's that close. Let's stretch this guy up here. Yeah. What we could do is we could always export to a spreadsheet. So we could actually see the values. Make that big. It's barely shown in here. So it looks to me like 0.973. And so that sign, the signs really bother me though. What about the angular velocity? Let's see. Let me show me that plot again. Yeah, that's still messed up as part of this. Let me just export it and see what the actual values are, because you can't really read this graph. It's Excel's. I mean, this SolidWorks graphs are terrible. I'm gonna sneeze here in a second. Okay, so we got 160. Yeah, and I said, what did I say that was going to be? Equals to that divided by 180, and then times pi. And I get that, like I said, 2.859, which is damn closer to 3 than my other calculation, right? So my conclusion is that, and let's see, we can just look at this guy. That's going to be a better number. This is a better number according that matches up. So it was the question of what sign conventions that I should have had, right? Should VA2 be a positive or negative number, and should VD1 be a negative number in this equation right up here? VD right here should have been have a sign convention of 1, right? And I think of negative. I'm really convinced of that. And then omega. And then this guy here should have been negative. Interesting. I wonder if there could be another mistake in the sign conventions up here, right? Well, for one thing, VD here, right? VD2, yeah, we still have that as positive because we assume the thing is going downwards. At least they show it right here, and they show it right here. They make it go counterclockwise right in here. It must have gotten a negative number. Huh. Interesting. Well, I probably messed up more people than anything else by doing this one now. But, interesting.